Alrighty, everybody, what is this? Exam 3 from fall 2017. This is a internal force diagram problem. We've got shear, moment, and this time we've got normal force, which I've probably told you a lot in platoons and stuff, and I never covered them. I don't think they're going to be on the exam. I really don't, because I've never seen them on the exam. I remember when I took the class, Mr. Hosting told us that we cover it, and it's kind of a bonus content, but it's not really expected to be on the exams. That being said, though, I am going to cover it here just to make sure that if for whatever reason they do surprise us or surprise me, that you know how to do it and that I know how to do it. So we'll go ahead and discuss this problem. But otherwise, this problem is not too bad if we take a look at it. So it says, compute all support reactions and label them on the figure below, this figure here. Draw the shear, V, bending moment, M, and axial force, or normal force, diagrams, N, on the spaces provided. For all diagrams, be sure that the local maxima, minima, and zeros are labeled and located. Well, that sounds like a lot, but ultimately, it's how we'd solve for them anyway. They just want to make sure we cover our bases and have everything included. So, excuse me, I'm kind of shifting around a little bit. I guess first things first is we solve for these forces. Well, if we just draw this and pretend it's our free body diagram, they don't ask for one, so we could probably get away with just drawing on here like it asked. We've got AY and AX, because this was a pin. And then we've got BY going up, because that's a roller. And those are the forces we need to solve for. So we'll go ahead and start at the very beginning. We'll take the moment about A, just so we can eliminate AX and AY and solve for B by itself. So some of the moments about A, we ultimately, if we look at these, we just need all the vertical forces of this total component, BY, and we'll include that. Kind of a bad way of putting it again. I'm not too great at explaining this type of stuff, but ultimately, first we'll start from the left and go on out. First, we've got this 30 kilonewtons, but we only want the vertical component. So we're going to have 30, and to get the vertical component, this is going to end up being a 3, 4, 5 triangle. If you took Pythagorean theorem, you'd find that would be 5. But it's something that you should hopefully know by now from geometry and this class even. So to get the vertical component, we're going to take it times 4/5. That's ultimately the same thing as taking it times the sine of whatever this bottom angle is, if that makes sense. We're just keeping it. We're not coming up with the angle, because that we would ultimately be taking the inverse cosine of that and taking the sine of that. We'd be back to where we started, which is 4/5. And that is going to be 2 meters away, going down, and it's going to be negative because it's going clockwise. And the only reason we want just the vertical component is if we split this off into the x component, the x component would not be causing a moment because it'd be in line with point A. Next, we've got the 32 kilonewton meters. And it's going counterclockwise, so it's positive. So plus 32. And this is one where moments, applied moments or moment couples or whatever you want to call this, they don't matter where they're acting on the beam. Wherever they are, that's their flat moment rate, I guess. It doesn't matter if they're on this point or here or on the very end, it's going to be 32 everywhere it is. It's already got, if you look at the units, you can tell it already has the meters in it, which tells us that it's already taken into account the moment, or not the moment, the distance happening on it. So it's just going to be a flat 32. Next, we're going to have our 15 kilonewtons, same thing as the 30, we just want the y. So we're going to have 15, and this is again going to be 3, 4, 5, so 4/5. And the total distance is going to be 2, 4, 6 meters away. And it's going to be negative again, because it'd be going counterclockwise, right-hand rule. And then we've got this distributed load here, which is going to be, again, negative because it's going downward on the end. It's going to be going clockwise, so negative 12. We need the whole distance this covers to get that into the whole force, so 12 kilonewtons per meters times 2 meters puts it in terms of kilonewtons. And then we need to know that for the sake of finding the moment, this is going to essentially be acting on as one big force in the middle of that. And so the big force in the middle of that it's going to be 1 meter from the end, but we're taking this from A. So we're going to have 2, 4, 6, 8, and then 1 meter. It's going to make it 9 meters away from A. So we're going to go ahead and put in 9 there. And then 1, 2, 3, 4. We've got 1, 2, 3, 4. Last but not least, we've got BY, which is going to be positive. It's going upward. BY times 2, 4, 6, 8 meters. That's all going to equal to 0. So BY, if we calculate this all out, is going to be, and this time in the calculator, since BY is positive here, we're going to punch these all in opposite signs of what they are. So we're going to have 30 times 4/5 times 2 minus 32 plus 15 times 4/5 times 6 plus 12 times 2 times 9. And then we'll put that all in parentheses. Since BY is going to be on this side, we need to divide it all by 8. We're going to get BY is equal to 38 kilonewtons going upward. And it said for us to label it on the diagram provided. So we'll go ahead and say BY is equal to 38. And it's drawn correctly. We don't have to change the arrow or anything. Now, we need to solve for AX and AY. Now, normally, if I were to solve for AY, I would take the moment about B. But I'm feeling kind of lazy in that, and I feel that in good faith I did this correctly. So I'm just going to go ahead and solve for it in the forces in the Y. I don't really feel the need to check my work, but in general, if you do have a lot of time, it'd be a good idea to take the moment about this point to find BY, and then take the moment about this point to find AY, and then take those moments, put them into a sum of forces in the Y, and it should equal out to 0. And that's a good way to check your work. For the time being, I'm just going to solve for forces in the Y. So we're going to have AY minus the 30 times 4/5. This doesn't do any forces in the X or Y. Minus 15 times 4/5 minus, and this is going to be 12 times 2. And then plus whatever BY is. So plus 38, that's going to be equal to 0. It's going to be AY. So AY is going to end up being, if we put these all on the other side of the equation. So AY is going to be 30 times 4/5 plus 15 times 4/5 plus 12 times 2 plus 38. Oops, my bad. Minus 38. Because this is negative, 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 and positive, we would flip them around because we'd be adding them to both sides to get on the other side. So 30, let me check over my work real quick. That looks pretty correct. And AY ends up being 22 kilonewtons going upward again because it's positive. So we can go ahead and write that in, 22 kilonewtons. Next, we can take the sum of the forces in the X to solve for whatever AX is. So sum of the forces in the X, of course, we have AX going to the right, so it's positive. Next, we're going to have the 30 kilonewtons, but it's going to be pointing down and to the right. So we're going to look at that right component. It's going to be a positive 30 times 3/5, because it's 3/5. It's going to be going to the right. Next, we're going to have the 15. It's pointing kind of to the left, so it's going to be minus 15 again times 3/5. And it should just be those two forces. Everything else is either a moment or acting straight up or down. So that's going to be equal to 0. So we calculate this out. We get AX is equal to 15 times 3/5 minus 30 times 3/5. We're going to end up getting negative 9 kilonewtons, or equal to 9 kilonewtons to the left. Well, I'm going to revisit our free body diagram here. We'll draw a little squiggly here. Our free body diagram here. We have AX drawn to the right. It ended up being negative, so that means it's drawn to the left. So I'm going to go ahead, and for the sake of this, because this is where we're reporting our answer on this, I'm going to go ahead and change the free body diagram and draw it going to the left, just for the sake of this. Now, on a normal problem and any other problem, it's fine to leave your forces, your unknown reaction forces, in the original direction you anticipated, and then just make sure you report what direction it's going in the end. But since we're actually going to use this in this free body diagram down below, I'm drawing it in this direction just to help me and you visualize it differently. So knowing that, this is where we get into the fun part where we actually draw our diagrams. So drawing our diagrams is just kind of knowing how the relationships work between this all the way down. First things first, they give us what each of these is. We got shear, moment, and normal. You always want to write units in. Whether you write units in with the numbers along this when you label your maxima and minima, or you label it off to the side, you need to make sure you include a unit. So I'm going to include it off to the side just so I'm covered for everything. So shear is just going to be forces, so it's going to be kilonewtons. Okay, I'm going to go ahead and do this for the rest. Moment is going to be kilonewtons times meters. And then normal is going to go back to just kilonewtons because it's just a force, not a moment or anything. So yeah, we go ahead and go into our shear. First things first, we have AY acting 22 kilonewtons straight up. So that means our shear is going to go straight up to 22. Whoops, I broke my lead. It's going straight up to 22. And then from AY to this dotted line that they gave you, which is very nice of them, there's no other forces applied. So it's just going to be the same. So it's going to be straight across up until here. And now we've got the 30 kilonewtons, and we only want the vertical component. So for here, it's going to be 30 kilonewtons times 4/5. And that's going to be the change. So we're going to take 30 times 4 over 5. That means 24. That means this force here is going to make our shear go down 24 kilonewtons from wherever we started. Well, we started at 22, so 22 minus 24 is going to take us down to -2. So we'll go ahead and draw that in. We've got -2. And then from here to here, there's nothing changing the force. But if we look here, the only thing here is going to be this moment. The moment doesn't change shear force either. So we're just going to go ahead and draw it straight across to this dotted line where we have another applied force, and this one will change it. And again, we have 15, but it's at an angle. We only want the vertical component. We're going to take 15 times, should be 4 divided by 5. And this is 12. So from wherever we're starting, we'll go down 12 because this is pointing down. So we started at -2. We go down 12. We're going to have -14. Okay? And then from here on, nothing really changes it. And this is where it gets a little bit more fun. So first things first, when we're at point B, we're going to include the BY going up, and it goes up 38. So 38 minus 14, or -14 plus 38, whichever way you want to look at it. It goes up, it pushes it up 38 to 24 kilonewtons. So you go all the way back up to 24. And then from here, this is a distributed load, which means that it's not all occurring at one point. That means that the change in the shear is going to occur over time. And so we need to calculate what this whole thing is to see what the total change in shear is. Well, we've got 12 kilonewtons per meter, and it goes over 2 meters. That means the total change is going to be 24 kilonewtons going down. Well, that's kind of perfect because we started at 24 on the left end. That means on the right end, 24 minus 24 is going to take us to 0, which is good because on the ends, you always want it to be equal to 0. We started with 0 on the left end and went up 22 because there was an applied 22. On this end, we want to end at 0 because it should end, we've got this pushing it back down to 0. And then from here, we can see that this is a distributed load. The value of this distributed load is going to be the slope of this line. So it's just going to be a -12. And it's a constant -12, which means that our slope is just going to be a constant straight line going down. And that is our shear diagram. We've got our maxima and minima labeled. And that should be essentially everything you need to know for the shear diagram. I like to label this as first order because we have a slope on it. So this would essentially be, if we were looking at our formulas again, it'd be negative 12 times x. It'd be going down. So that'd be first order. Well, now we need to find what our moments are. And in order to find our moments, we need to use information from our shear diagram. So what we need to do is we need to split this off into multiple areas. We've got area 1 here, area 2, area 3, it's a bad 3, area 4, and lastly area 5. And these areas will kind of show how the moment is changing in the similar way that how this distributed load showed how the moment was changing. Well, we're going to have to go off to the side here and calculate what these are. So area 1 is going to be 22 times 2, because the width is 2, height is 22. And that's going to be 44 kilonewton meters, and it's positive. Area 2 is going to be negative 2, so it's an equal sign, negative 2 times 2. It's going to be negative 4 kilonewton meters. Area 3 is going to be, again, negative 2 times 2, because it goes, these are all 2 apart, which is very nice in this problem. Oop, negative 2 times 2 is again negative 4 kilonewtons times meters. Area 4 is going to be, we've got a negative 14 times 2. It's going to be negative 28 kilonewton meters. And then area 5 is a triangle. So we've got the height of 24 and the base of 2, but we need to divide it by 2, because the area under the triangle is going to be half of the base times height. And these 2's are going to end up canceling out, so it's just going to be 24 kilonewton meters. And it's positive because it's on the top of this axis here, and because, or you could look at it in terms of both of the values are positive. So these are our areas, these are how our shear is going to be changing. Well, this is where we need to look at here. So we always start at 0, we always start on the left end, we always start at 0. Well, what we found from area 1 is that area 1 is equal to 44 kilonewton meters. That essentially means that over the course of this entire distance here, the shear in it is going to end up causing a total change in moment of 44 kilonewtons. So from the left end to here, we're going to have a moment of 44 at the right end, and it's going to be positive. And then, just as we looked at before with the distributed load, the slope of the shear, or I'm sorry, the value of the shear is going to end up giving us the slope of the moment. So the value of this is 22. That means the slope of it is going to be a positive 22. So that just means it's a straight line up to 44, which makes sense because with a positive slope like 22, if you were to multiply it out by the total length, you'd get up to 44 anyway. Next, if we look at here, it's just another force. We can use our area 2 right here, and it's negative 4. So that means over the course of this entire thing, it's going to take us down to 40. And it's a straight line again because it's a negative, or I mean, sorry, it's a flat line up here. So it's just going to be negative 2 is there. Straight line there. So from 44 to 40. Now this is one thing where when I was taking a look at your quizzes, this is something that a lot of folks missed, is the direction that the applied moments cause the moment diagram to go. Essentially, the direction, or I'm sorry, the applied moments, just how the applied vertical forces change the shear. The applied moments are going to change the moment, and they're just going to be a jump, like a vertical curve, a vertical jump. With the shear, it's very easy because when it points down, it just makes the whole graph point down. Well, moment is almost backwards to how you would think about it. So we have always taught you that in convention, positive moment is counterclockwise this way, and then negative is that way. Well, if we look at this, this is a positive moment, but with the convention on how we make our moments jump, this would not make the graph go up, it would make the graph go down. So we'd have a total change of negative 32 here. So from 40, go down 32, it goes to 8. This is something, let me rewrite that 8, it's a little hard for y'all to see. It go to 8. This is something that you just, again, kind of like internal forces in general, you just need to memorize. If we were to take like a cut here and sum the moments, you would end up finding out that this moment force would cause this moment to go down 32 anyway. I'm going to draw a little example up above that I just thought of. So if we had 32 here, let's just pretend we don't have any forces here. And this is a cut, so we'll have an internal moment here. I'm just going to write it as M cut. Well, if we were to sum, I'm going to do it off to the left here, sum of the moments about cut, we're going to end up having a positive M cut and a positive 32, and they're going to equal to 0. Well, essentially, M cut is going to be equal to negative 30. Oh, wrote that backwards, my bad. And negative 32. So, if I bring that closer and focus on it, just taking a look at that, that's kind of how we visualize it. That's why we show that this negative 32 here makes it go down. Because if we were to cut it into a section and do internal forces from that and make our formulas like we would normally, we would find out that the moment would be decreased by 32 by the applied moment. Now if we had the 32 going in the opposite direction, in this formula here it would be a negative 32, which means that the moment of the cut, the internal moment, would be positive. So I hope that clarified things for you. Otherwise, you might not have time to reason through it on the exam either. It's just something you got to memorize. It's very vital to how you do these problems. It could make or break essentially your moment diagrams. So it could be the difference between them lining up to 0 on the end and being completely off. Excuse me. So just make sure you memorize how those work, or if you don't memorize them, try to reason through it. I had a math teacher once who said, don't memorize things, just know how to solve for things in a quick fashion or whatever. So hopefully you guys can either memorize it or know how to reason through it, but just know that this would make it go down 32. The next thing we have is area 3 right here, and this makes it go down 4. So we go from our 8 minus 4, it's going to take us to 4. This is actually a line down. It's not straight. It looks kind of straight, but it's a very small values we're working with here, so it's kind of hard to tell. Next, we've got area 4, which is a greatly negative number, negative 28. We'd take our 4 minus 28, which would take us down to a negative 24. I'm just going to draw a line. Again, I would suggest, I would suggest you guys using straight edges for this, so you don't do what I just did. I'm just kind of lazy right now, unfortunately. But yeah, use a straight edge from these points just to make it easier on yourself. So 4 minus 28 takes us down to negative 24. And then last but not least, we need to take into account area 5. The total change from area 5 is going to be 24. So we take our negative 24 and go up to positive 24. But the difference is, unlike all the other areas here, the slope on the shear here is not constant. It is decreasing. Or I'm sorry, the value of the shear here is not constant. It is decreasing. So it starts at a very positive 24 and goes down, down, down all the way to 0. So that would be reflected in our slope here, where on the left end here, we would start with a very positive slope, a slope of 24, and it constantly decreases to 0. So you don't have to be perfect, but just draw something that kind of looks like a curve. And of course, if I had a straight edge, it would be more pronounced there. But this is a curve, and it goes up to 0. And I think that's everything we need to do. Of course, you're going to want to do labels, so I'm going to label all the first orders by writing first order here and drawing a line. The reason we do that is for cases like this one and this one, where they almost look vertical, or not vertical, but completely horizontal, but they're not. And so by pointing our arrows, that lets the grader and other engineers know that, yep, we know what we're talking about. This is actually going down. It's not straight. So our pictures can't be perfect, but labeling them helps people see. And then this one is going to be second order. Essentially, it's because it's kind of exponential. Essentially, just know that wherever it's first order on here, it's going to be second order here. The orders just keep going up from shear. So if we had, for example, a fifth order on this, it would go up to sixth order down here. You're never going to see those orders because those are ridiculous, but just know that that's the case. And then the next thing we need to label is where this is equal to 0. And that we'll just say is x. Well, in order to label where that is equal to 0, we have a couple of methods. One method is to look at this beam and make a cut somewhere in here and then draw this whole beam and do internal forces and internal moments and sum of the moments to find where the moment would be equal to 0 here. I don't feel like doing that, and you don't really need to do that because we have an easier method. Since this is a straight line here, we can go ahead and just use geometry. So what I've shown you guys before is I'm going to write about slope. So slope is m, typically. So slope is equal to rise over run. Well, in this case, we have the slope, which is our negative 14. We have our rise, which is 4. We don't have our run, which is x. So we're going to essentially solve for run by doing run is equal to a little maneuvering here, rise over the slope. So that means x is essentially going to be 4, and I'm going to go ahead and write the units because it helps you see it. Kilonewtons times meters divided by our slope is the negative 14 kilonewtons. And get our calculator out. It's going to be 4 divided by 14 is, oh, that's an ugly number, 0.28, let's say 57 meters. And again, I wrote the units because these cancel out, shows you it's in meters. And my bad, I shouldn't have drawn the slope as that. It doesn't matter essentially what the slope is as long as you show, because the slope is going down, it's going to go down this way. Because we can't have really a negative x, just the magnitudes of them. Which doesn't quite make sense, but that's just how you do it. So that's our 0 here. We've got x labeled down here, so we don't really need to label it here, especially since it's so close quarters. And we don't really need it to make a calculation later on anyway, because from here on we just need the axial diagram. And we can do axial diagrams similar to how we did our shear diagram before. So this is where you could use your relationships, or what I'm going to be doing is I'm going to be doing kind of what we did with the moment up here, is we could kind of visualize what a cut would look like to show what the internal force would be. So I'm going to go ahead and start here at the very left end as we would. We have AX going to the left, which is 9 kilonewtons. Well, for convention down here, I'm going to go ahead and draw what a cut would look like. And cut. And we have our 9 kilonewtons here. Well, if we were to take a look at this, and this cut is going to be somewhere in here, we should know that no matter where we go, the shear should be, or I'm sorry, not the shear, the normal force should be 9 kilonewtons is the magnitude. Now I'm just trying to figure out, is it positive or is it negative? And this is something that you should remember or memorize the conventions. If not, do what I'm doing here and just kind of visualize what a cut would look like. If we take a look at this cut and we sum the forces in the x, we end up getting that the normal force would be a positive 9 because this is going to the left. Well, knowing that, we can know that this would go up to 9 here. And then from A to the next force, there's nothing else that would change the shear, or the normal, so it would be flat. And so, using what we learned here, we kind of essentially learned that an applied force going to the left gives us a positive change in normal force. I didn't have that memorized beforehand, but I was able to reason through it. Now, though, we can use what we learned here to help us in the future. So here we have an applied force going, it'd be pointing to the right if we took just the x part. Because it's going to the right, we would end up having a negative change in the normal force. And that's just based on what we learned here. If we were to draw another diagram with the force applied, we would see that it would end up going down because of it. So this applied force is going to end up being 30 times 3/5. So it's going to be 2. We're going to have a change of negative 2 going down. So that's going to take us down to 7. And then from here on to this next force, there's nothing that would change the shear. So we're going to go ahead and draw a straight line all the way across. And then next, we've got 15 kilonewtons. Hang on, just one second. Okay, my bad. I kind of messed up a little bit on this, and it wasn't quite looking up right how I want it to be. Go back to that. I calculated it wrong. So, looking at the change caused by this 30 kilonewton force at an angle, we would have 30 kilonewtons times, and then this time would be 3/5, which would be change of -18. This past time I did divided by, and it gave us 2. That's not correct. You're going to multiply it. So multiply this by whatever the fraction would be, and that's how you get your direction. So we would have a change of -18. So it would take us down from 9 to -9 here. And then it would go straight across to here. From here on out, we've got our 15. We would have 15 times, and then to get it horizontal, would be 3 divided by fifths. 15 times 3/5 is going to end up being 9 is the magnitude. And because this is pointing left, as what we learned down before, if it points left, it's a positive change in the normal. That means that we're going to go from -9 going up 9. Damn it. Sorry. Mind my language there. -9 going up 9 to 0. I apologize for that. I guess on YouTube I can't say it's made for kids anymore. But here we've got the normal force is equal to 0. And if we were to look at the rest of this, there are no forces going to the left or to the right. So that makes total sense. That means our shear, or our normal force is going to be 0 from the end, from this to the end. And that's really all you guys need for your shear and your normal, your shear, your moment, and your normal diagrams. Like I say, normal diagrams, I don't really expect them to be on here. I definitely don't expect torque diagrams to be on there. Maybe it's a good thing for you to review a couple times, but I don't want you guys wasting a lot of time for something that probably won't be on there. At the same time, I don't want you guys not studying it and then being surprised. So it's kind of up to your discretion. I don't expect it to be on there, but honestly, when I took this exam, I don't think I studied axial or normal at all. Because like I said, I think Hosting told us it would not be on there. But putting that aside, this is all you guys need. You guys need to make sure you label maximum and minima, put your units in, label your orders. Those are definitely helpful. And otherwise, the rest is just kind of knowing how to do the areas and knowing the relationships here. And like I say, if you don't have the relationships memorized, you can reason through it like we did here, and then use the reasoning you learned from here, find the pattern of that, and apply it to the rest. So like we said, we found out that if this is down, or the moment go down, then we could use that, find that going counterclockwise would make it go up. Kind of same as this, we found out that left makes the normal go positive, so going to the right would make it go negative. It's kind of confusing maybe how I'm saying it, but ultimately this practice makes perfect. I hope you guys work through this problem and some other problems you can find in the textbook, and that's how you're going to do well at this. Otherwise, that's all I have for you for this problem, and as far as I can tell, that might be the last exam problem I'll be doing. So hopefully these were helpful for you guys. Let me know if there's anything wrong, if there's any other ways I can help you, or other videos you guys want to see. But that's it. Good luck with this. Happy October. It's the last day of October. Good luck with that. Enjoy the weather. It's a beautiful day. If you haven't yet, you're probably watching this later too. But good luck studying and good luck on your exam. You guys are going to do great. I hope you do. We'll see you.